Hey everyone, Michael from Bright Musical Circuits. This is the ye old CMOS Chime. We're going to go over the schematic today. These are the oscillators here. This is the VCA here. And then this is the envelope generator down here. And we're going to go over this piece by piece, starting with the oscillators. So the oscillators are what makes the sound. These are inverters. CMOS inverters. In like Boolean logic, it takes a 0 and outputs a 1, or it takes a 1 and outputs a 0. Voltage-wise, this would be either ground and plus 12 volts instead. So the way this works is these all have capacitors on their input pins that are going to charge or discharge through the resistance of our frequency knob in this 2.2K based on what the output is. And so let's say we start off with its discharge, we have 0 volts here. That's going to set it to plus 12 volts up here. So with that, current is going to flow into that capacitor, and it's going to have voltage on the input pin slowly rise up until eventually it gets to a high enough point that it's going to then change the output back to 0. At which point, this will then be a discharge path instead of a charge path, and so the voltage will go the other way out of the capacitor until eventually it gets low enough that the output will then go back up to plus 12 volts. And so that'll continue back and forth, and you're going to have these sharp changes in voltage on the output, which are going to form pulses, or pretty close to square waves. Yeah, this is just like any kind of low-pass filter or something like that. The amount of current that change you're going to see on that capacitor is just dependent on resistance. So when you have low resistance, it's going to go fast. High resistance, it's going to go slow. That 2.2K limits it to make sure you're not going to like go up above the human hearing range. The outputs of these go through 0.1 UFs. That's going to take off the, instead of being 0 to plus 12, it'll now be plus 6 to minus 6 doing that. And then all these outputs get mixed together through these 100K resistors, and they meet down here at the VCA. Outputs 3 and 4 also have these toggles. These are wire pads that go to toggle switches, so that's, a little knock there. And that is the mute switch, that you can just toggle it so that these are disconnected and no longer part of the circuit at all. So next we get to the VCA. This 1K resistor is going to attenuate down the signal that from all those outputs to a small enough signal that it's not going to immediately overload the transistor and put it into saturation. Without going into too much detail on how a transistor works, basically the voltage difference between here is going to affect how much current flows through the whole thing. So we have our control voltage down here. The lower that gets, there's going to be a higher difference in voltage between this, and that's going to increase our gain. The higher it gets, the closer there is here, and the less current will flow and less gain is going to happen. And we have 2 of these here. The second one has its input grounded, and so it's only going to see the difference between ground and the voltage down here. So our voltage down here is CV here, that then goes through this resistor, and then there's a different voltage that's different from CV down here, which is going to be dependent on how much current is flowing through these. And it's that current that is going to tell this how much current to flow down through here. But these are going to be out of sync with each other because this is getting an inverted version. So yeah, this will have current flowing down here while it's up here because of the way these are coupled. These 22K resistors, these give you a load. So a voltage is able to form up here. So while this is negative, this would be a positive. But these would also be a little bit offset positive because they're going to be so close to the 12 volts here. And the offset would also change based on the control voltage. And so we use this differential amplifier over here. That is going to make it so you only see what's different between the two. Any offset that's common from the control voltage is going to get removed. And then we just have our output jack goes to this wire pad. The 1K there is just safety. And then this 10K sets the brightness of the LED. We're taking our LED from the audio output, so you will see some flickering in it, which I just thought it kind of looked cool, which is why I did that. Yeah, finally we have our envelope generator. This has the loop function. So the loop toggle is loop A here, loop B here. That's going to act as an input for our envelope generator. We also have our gate input here. It's got that diode, so that way if you input an LFO that goes negative, only the positive voltage is going to affect the input here. So that way if you're using multiple inputs, you wouldn't have to worry about, the negative LFO canceling out your trigger input. The trigger input is here. It's different from the gate in that it uses this capacitor. We have our 100K pull down resistor that is putting things at ground when there's nothing input, but that also creates a high pass filter of this 0.1 capacitor there. And so that way a gate that looks like that is going to get then filtered, high pass filtered down to just being the transitions like that. So you'll have these really short pulses whenever you're making a change. So the comparator that these are all going to is set up as an inverting comparator. Its threshold is 0.12 from this 100K 1K voltage divider. So when the voltage goes, so this is normally going to be high over here when this is at 0 volts, and then when it goes above 0.12, it's then going to go negative. And it'll be for usually a really short time if it's the trigger, just long enough that it will then take this capacitor down to negative 12 volts. And then that negative voltage on the capacitor is going to drain through this 1K and 1 meg decay pot until it goes back up to 0 volts. And the reason we're using a backwards capacitor and a inverting comparator is because we wanted a negative voltage to begin with for our VCA. So all we have to do is buffer that voltage to send to the VCA, and then we can also send it on to this Schmidt trigger here for the loop control. So this is basically a comparator with a little bit of feedback to it that after you go past you have to go a little bit further past the threshold in order for it to do it. And the reason we're using that instead of a regular comparator is that when we want this to go positive for a long enough time that it can send signal back through here to then recharge this capacitor all the way. We're getting our feedback from this 1 meg resistor, and then we have a 10K input resistor that's attenuating our input down a little bit. If you wanted to change your pulse time, you could make it so that the 10K was a little smaller. And that's basically how this whole dang thing works. Other than that, we've got a couple gates that we grounded out. Power connectors are here. It's my basic thing. 10 UFs on the input. 10 ohms on the input. 10 UFs to filter that. And then caps right on the pins. And the CMOS is powered plus 12 and ground. The op amp is plus 12 and minus 12. But yeah, that's pretty much everything. Thank you for watching.